Alright. This is, okay. Let's go! Alright, so today, we're building, we might be building this thing. I don't know. Well, actually, let's go over to the other thing, that I've already finished. And I haven't shown this off yet, and I'll show it off in another video, but I did want to mess around with it a bit, because, yeah, I'll show this off in a future video, but really, this is what I've been working with recently. I've been working on this thing, making this thing work. And this thing is all good, and it is okay. It works, kind of, but it's terrible. I mean, look at all these repeaters. These are just garbage. There's way too many repeaters in this thing for it to be worth the time that I spent making it. Not even to mention that it doesn't have a functional registry that I'm happy with. I mean, I am happy with this. This is okay. It's not what I want. I want something better. So that's what I'm gonna work on. The next thing is better. I mean, there is another issue with this thing. This is massive. This is too big. So I have came up with a few solutions. I'll go ahead and talk about that now. So over here we have a 16-bit adder. Well, actually, it's more like it takes 32 bits of input and then can add all of that. But it is still technically a 16, because you could technically, if you fire only one. Why did I get a notification about myself being live? Why? I mean, at least I got... So, yeah. Oh, hold on. There might be a problem with these last ones. I need to go check the first ones and see if there's an issue with this. Okay. I forgot a redstone dust here on these ones. These are XOR gates, by the way, and I've made them smaller. I've made the gates way smaller on this design so I can fit more into a tinier space. Which this is gonna be the arithmetic logic unit. It's gonna be the whole thing, just this entire space. I won't even go out to build the logic unit. I'm just gonna build the logic unit on top of everything else. So basically, it'll be able to add, perform AND functions. We'll be able to perform other functions on top of that, and more functions on top of that. And it shouldn't be too big. It should be decently sized. Hopefully. It is the hope to have this thing functional and work properly. All right, let's begin. I need to perform a test on all these, and I also need to set up the redstone buses on the top of these as well, just because I haven't done that yet. I spent all this time building the thing, but I didn't set up the buses yet. Which these should be able to handle the A and B. I think I've tested up to 8 of these already, so 8 of these adders have been tested. There's a total of 16, so it is, I think that is a way of classifying it as a 16-bit adder, because it does output 16 bits as well, and it can take in 16 bits. It can also take in 32 bits if you wanted. We're getting somewhere. We're getting to these big numbers. Eventually I'll have a 256-bit adder, but at that point, I don't, like, you see, here's the thing. When you get to a larger and larger number of bits, it takes longer to do all the functions and stuff for that. So that's why, like, hello, welcome. Welcome to the stream. I see we have one person joining us. There is a bit of latency, so yeah. Just all right. So I think the first function we're going to add on top of these is going to be the AND function. And then on top of that, we'll do NAND, because that should be pretty simple. And then on top of the AND and NAND functions, we could technically fit all the functions side by side and on top of each other if we want to squish it even more. Instead of just going with like what we did over there, where every function takes up like a 3x3 block. It is quite annoying, these other functions. Let's go ahead and... So all these, see how all these logic units, they, yeah, each individual piece of logic here is taking up a bit of space, but we could just do a, for AND, it's just like this. We just squash it down a bit, and takes up that much space if you do it vertically. So we could technically shove an AND gate there, and then we could invert the output as a NAND gate. It would work pretty good. Oh, wait, we need to do that differently. That needs to be... I think it needs to be like this. I don't remember how I built them over there, but I think it's like this. So that, and then that. Oh, there we go. That's AND. Yeah, that's what I remember building. So the NAND could just go next to it, and that'd be NAND. Well, it would just be NAND by default. So that's NAND. I don't have to add another torch. So that'd be how I'd fit it next to each other in the new system. And then I could do OR or NOR, or the inverse of NOR. And I could fit XOR or XNOR on top of each other, or next to each other. That would also work. So I could just do the gates and their opposite on the same layer next to each other on top of the adder units. So that will be a good simplification of or compacting of all the systems in this thing. Which I'm excited to do this because it's big progress for me. Especially since I finished my first one, I've learned all the things that I've done wrong. They are big issues, and I can easily learn from my mistakes in that one and make it much better in this new one. So we'll keep doing this thing here. Okay, let's go ahead and set this up. I really need to finish all these buses. And then I'll go press all the buttons over... Actually, no. I really want to mess around with that thing and see if I can make it do anything cool. But, I mean, I've done that in the video, kind of. And I've already recorded the video. I'm not gonna... You know, I'm not gonna spoil the video anymore. It's all about that big computer over there that we've finished. And, I'm not showing that off today. Because that'd be, we're saving that for later, okay? That's the dessert, okay? That's the icing on the I don't know. What do you put icing on? Okay. So, each of these... Hold on. I could explain some things while I do this, because there are some things I failed to explain very badly. So, like, why are we taking 2 bits? Like, is there... Why? Why 2? Well, you could do 3, but most logic units, it's simpler to just do 2. In a 3-bit system, it would actually be... So, if you take in 3 bits, you'd have a A, B, and then you'd have the other bit, which is, you know, we'll just do this. Okay. So, it'd be different to add these, and I'm actually interested in making a system that uses 3 bits for its input. So it'd have a positive one, but I'm not sure how we would identify whether it's positive or negative. And then we'd have a negative one, or like this would be 0, this would be 1, this would be negative 1. And then we'd have to figure out how to add them together so that way they could be balanced. So basically, this is called a ternary system, I think, or trinary. I'm gonna call it trinary, but it's actually probably ternary. And basically, this is base 3. Binary is base 2. You only take 2 inputs. And why is binary, you know, 2 inputs? Why is that simple? Well, because it's either true or false, okay? So, you either have a statement that's true or false going into here, and then, you know, it's easier to do it with 2 because you only have to work with 2 things, okay? Just trust me on that. Now, in a one of these systems, you can either have 1, or 0, 1, or 2, or you could do it opposite or differently, where it's a plus or minus 1 or 0. If that makes sense. That probably doesn't make sense because I'm explaining it, and anything I explain ends up just being a bunch of words for no reason. So, basically, on base 10, that's what we use, because we can count up to 10. There are higher bases. There's I've heard of base 64, but I don't think that has anything to do with it. So if you could count up to 64, and then that's when you carry over, then that'd be base 64, basically. So, the reason why we don't code in base 10, I don't know why. I mean, I guess it's easier for logic gates, because you don't have to have as many inputs for the logic gates. It just makes it simpler. Now, there was a Russian guy, right? And this is the reason that, or this is the thing that inspired me to actually attempt to build a 3-bit system instead of a 2-bit, like most of these other systems, is that he basically built a computer a long time ago, and it used 3 inputs, which was the +1, -1, and a 0. And that could be pretty interesting. I'd have to look at what he did to make his system work, to make my system work, and I could, that would make it simple, but still, there's a lot more you can do in real life than with Redstone, and it's a little bit more simple in real. Well, actually, it's different in real life when you yeah, because in real life we have relays, vacuum tubes, and all kinds of other complicated things that perform basically the same things for logic gates and stuff, and transistors as well. Which transistors are what we're currently using, like right now. Your computer is made of transistors. Ha! Take that. Well, it's probably not transistors exactly, but it's the offshoots of the science of making transistors. It's semiconductor type things. So yeah, that's a lot of stuff I just talked about, and I'll let you all absorb that while I just do some building here and create this. Why am I doing this? I'm not adding another. Hold on a second, I could add another adder unit. Anyway, so my new system's actually going to be able to flip the bits and allow me to do subtraction. Hopefully. Oh yeah, we were going to test this thing, weren't we? And we need to test this thing because that's good. Okay, we'll just go ahead and fire these off. So I've already explained these. These are adders. Full adders. So when these first two fire, the next one should fire. And when this next one fires, it should just carry over to the next one. What if, because it carried. So it's added 4 bits now. Yup, there we go. We got 4 bits. Well, that's actually not 4 bits, but in English, I'll put this, this is the number, I think this is 6. So basically, 4 bits makes up, wait, no, it makes up a nibble, which makes up, that's part of a byte. So 2 nibbles is a byte, which is 8 bits. So just 8 bits is a byte, and that's a lot of bits, especially considering that these are. Oh, hold on. If I do this one, does that one? Yes, that is exactly how it should. That is the next number. So boom, boom. Now for this new system, I'm gonna have a ROM. Now what is a ROM? Well, let me explain it. It's a read-only memory. And that will allow me to program the system. And I was like, why the heck would you want memory that you can only read? That's what my old system was like. I was like, why would you want it so you can only read it, but not write it? And so this computer basically writes itself over here. This is just the garbage. This is a mess. It's not good. So my new system will not add itself. It's gonna be good. And not do that. Oh, and the control unit over there. Don't even get me started on that thing. It's just terrible. But it was my first project, and I didn't want to throw it all away just because I thought it was bad and not going good. I mean, I probably should have instead of wasting all my time on that. And everything seems to be going good. Everything seems to be carrying over. Now, if we did fire the initial carry-in bit, this would actually turn on. So yes, it's good that everything is carrying, because now I don't have to worry about the system being broken. In the event that one of these gates is wrong, then I'm probably not going to notice it. And I'm going to have to, hopefully, one of you all will notice it for me. And I'm going to make sure to go through and be as thorough as possible with checking these things, because I did just rush through making them. Okay, does that one flip? Yep, that one flips over to there. Okay. So yeah, this is going to be already, this is already way faster than the other computer. Probably not for the addition part, because there is like, we are running 16, so it's gonna take like ages to actually run the system. it's not the fastest adder in the world. I'm sure there's better ways to do addition instead of just carry the bit over to the next one, but this is the simplest way of looking at it, because the green line is the carry, and both the orange gates are AND gates. So you may be wondering, why do I already have logic gates if this is the adder part, not the logic unit? Well, you need these to actually make it function. You need 2 AND gates, an OR gate, and 2 XOR gates to make this function. And for an OR gate, you just need to have like a redstone wire. It's literally that simple. So the OR gate is right here. This green bit is, this green part is the OR gate, and it carries out the carryover. Very simple. Very simple. Uh-oh. That should not happen. So what is going on here? It's carrying over. Right. Yes, okay, it is carrying over. So that one's off. This one carries it over. Yes, it carries it over. When the blue bit fires, okay, we're missing redstone dust. That's the problem. That's the whole problem. It should be turned on when this one's on. So now we've successfully test fired this system all the way up to the what bit is this? I don't even know what bit this is. Well, we've already definitely got one byte through there, so. Oh yeah, that's the first bit of the second byte. Alright, there we go. That's another one. And there's another one as well. There we go. Another flip. I'm gonna try to see if I can go through this as fast as possible so I don't have to continue wasting time on this when we could be doing more productive things like building the next part, which is the logic unit. Flip that one. Okay. But I want to make sure this thing is functional and I don't have any mistakes like last time. I did have a few mistakes on the last one that I noticed after the fact. But hope they weren't too noticeable until yesterday or this morning when I recorded. And this morning, yeah, I left a few torches in from the testing. So I was testing out the data buses to see if it was actually taking the data from one side to the other. And yeah. I've actually learned a lot from the first computer that I made. And now I know that the first computer I made was terrible, but this one is going to be better because I know what I'm doing now. I'm going to hopefully this one is going to have more than just a random access memory. I don't even know what a RAM does yet, but I'm going to find out at some point. The RAM and the ROM, the most important pieces. Oh, except for the CPU is important. I should not say that. They're not important, but they are important. That should turn it off, and then this one should toggle it on. Now, I am happy with the innovations I made on the previous computer, because I will carry some of those ideas over. The idea that the overflow bit can actually toggle a multiplexer, which causes it to switch or fix itself, is a good idea. I like that idea. It's definitely good. It's worth the time of implementing that feature into a control unit. And I've also learned what flags are. Flags are interesting. I'm not going to explain flags because the words are not going to come out of my head right because I have not said it before. So, basically, a flag just tells it what to do. That's the simplest way I can say it. It tells the control unit something, and then the control unit decides what to do with that. But it's best to not think of a computer as thinking, in my opinion. It's better just to think that it does whatever you tell it to do. It performs an action based on the input is given. Yes. And the flag would be the input that is given. Okay. So now we have a functional 16-bit addition unit. Okay, that's 2 bytes of information there. We have 2 bytes, and I want to be able to store a lot of bytes because I feel like that is something that is cool. Storing more bytes is cool. I'm not even sure what... Here's the problem I have. Whenever I build these amazing projects, I have no idea what the purpose is, and I think that's a problem. I think I need to know what the purpose of my endeavors are. And also, I'm gonna have to, instead of shoving it in side by side, I don't think that'd work. I think... Okay. So this should actually, if we buy this one, it should power that one. That's not my problem though. I just wanted to show that off. The problem I'm having is what the heck? So we could actually fit an OR gate here, which is cool. I guess I don't. This could just be the OR gate. One OR gate right here. Boom, OR gate. I'm having trouble thinking how we're gonna fit all these pieces together because there is a lot of pieces that are going into this, but we need an AND gate as well, which is gonna be difficult to fit in there. But basically, we take. So we could have the OR gate here. We can have the. But the problem is that this one or this one could actually interfere with each other, and that's gonna be a problem. So I think we just keep them separate, and that would end up with us stacking them, which is not what I want. I do not want us to stack anything. I want us to keep everything individual. So I want, like, this. Just individual pieces. Okay? So I think we'll just make those ones pink because those are going to be the AND gate. We'll just keep with the same color coding. This thing is going to get really tall really quickly. And that's my main issue with this design, is that the way we're going to have to stack all these units. So it's going to get about as tall as the other one. But hopefully we've condensed it down enough that I don't have to worry about doing a ton of wiring. Like, literally. So over here, on this old computer, we have all the blue bits and all the red bits. They're hooked up like just a mess. This is just a mess. Like, I mean, it gets okay over in this area, but this is also a mess. This is disgusting. Because once you get up to here, it just all becomes spaghetti. It's the problem with my machine. It's too much wiring, over too much of a distance. And as much as I want to think that this system was smart, it is smart. It is for its machine purposes. It's not what I wanted it to do. And it is pretty nice to look at. I do have to admit, this is a beautiful machine. This would be great in a survival world for a base. But this is not what I want. This is not the system I'm gonna have. Although it can store 128 bits in each register. Well, actually no, it's 64 in each register. And these aren't even registers. These are more like just cycle memory. I don't even know what this is. I'm just gonna call it cycle memory. But it is technically a register, I guess. It's a bad register. I'm gonna press the button. This machine is just so much regret. So we'll just switch those over and check out what happened to the multiplexer. It probably did something interesting. Nope. Anyway, the next episode we'll talk about this machine. I've said that a million times, but I'm not gonna talk about this machine right now because that machine is not right now. Okay. So, and gate. Oh, I could shove them next to each other. Yeah, that's genius. I could totally fit them together. So, and we can fit the and this thing next to each other. Multiplexing this is going to be a bit complicated, but I'm sure we will be able to fit this all together. In fact, I'm going to keep it simple. I'm not going to try to put more gates in here. This would be more complicated to shove more gates into here. But this is gonna work pretty good, I think. Oh wait, that's not an AND gate. That's an OR gate. That's what? Wait, what does the other one have? The other one has NOR gates, right? As AND, OR, NOR, OR. I think I wrote it down over on the other thing. I think it should have an OR gate and an XOR gate and a not A gate. Which we can implement those. We can add not A and not B. That's the good thing about the system, is that because I was complaining about that with the last one, it was too convoluted to fit all the bits into it. Okay, we had an XOR, XNOR. Why not have OR and NOR? Don't they do the same thing, but they're different, but it like inverts the output. I think we can do that. We can have all the functions that we need. We can, you know what? We can even include the most useless logic gate for computers ever. But I actually have made a logic gate that does something that no other logic gate has done. Maybe. This is the first time. I'm gonna say this is a first, but I call this gate the this converse non-implication is what the gate does, because whenever this one is on, it turns off. Whenever when they're both off, it's off. When this one is on, this is on. So that would be our B input. So that would be, or no, A. That would be our A. So if our A is on, but not the B, then it's on. And only then is it on. So that's what Wikipedia calls converse non-implication. Trust Wikipedia. Okay. Okay. So, yeah, we could even put that gate in there. I don't even know that would do. That would... Why would I even want that gate? I don't even know. But we could cram every single gate in this thing, and then it would be the most amazing thing ever. There's no purpose in having every single gate. Maybe. Well, there's only the basic gates that everybody talks about every day, like and, or, nor. Those are the most important gates. And the other ones, XOR. XORs are pretty important. You see, you can't build a computer without XOR. XOR is used for the addition. Now, I would think there's a full subtractor, but actually, you just use a full adder, and then you just reverse the bits. Ha! Take that. Okay, there we go. Now, this is interesting. This is, okay, there we go. We just, do this. And, no, that would cause a loop. That would cause a loop. We don't want that. We don't want a loop. We need to fit this system somehow into a, this thing. So, I'm thinking we just, shove both of those in there. Power this thing. And that keeps the gate up here, so they both need to be off. When they're both off, this will turn on. And then, boom, now we can shove both the gates into the system. But that doesn't work for me, because I want it to be the other way. I want it to look nice. I want it to fit next to each other, so I can have my AND and my NAND right next to each other. So when they flip, it just makes things a little bit weird, or closer together, I guess. I don't know. I don't know why I want it to be the way I want it to be, but it just has to be the way I want it to be. If that makes any sense. We could put... I don't know, we can't put this lower. We need to put this up one, because there's no space between these two layers. Well, unless I want to cram them together, and that's what I want to do. I want to cram these things, as much of these circuits into each other as possible. Look at that. That works. But it doesn't work the way I... Well, technically, we could just shove it in here like so. That works. Yeah, that's, that works. That works for me. That's just how I want it to be. Just shove it in there. Boom. This is good. This is good. So that's AND, because both these need to be off for this one to turn on. Wait a second. Is that yeah, that's AND. That has to be AND, because both these need to be on for this to be on. The opposite would be NAND, which is going to be magenta, because magenta's a nice NAND-like color. Then we also have purple, which will be our OR gate, and our NOR gate's going to be another color. I like color coding things, okay? Don't ask why. It just looks better. You know, I probably should have titled this stream something interesting, like building 16-bit full adder. Oh yes, this is most interesting. Ha. I need something that screams interesting for my next video, I guess. I don't know. Nope, not like that. I think everything should have the same amount of delay. Everything needs to be synchronized. Because if it's not synchronized, then all the computer people who make actual computers in Minecraft are going to be annoyed. Because it won't be synchronized. Like, of course, it didn't really matter with the old computer, because it was all manually done. But I've learned things. Okay? Okay, now this is working, because they're both on, this one's on. That is how an AND gate works. That is how an AND gate works. So, now, whenever they're, you know, whenever one is different from the other, yeah, this will make it way more difficult to multiplex, actually. Because now, the well, no. It would take a bit more to multiplex it. So the way I'm thinking I'm gonna go about multiplexing these, oh no, this is gonna get convoluted when we go to multiplex these things. Because how am I gonna cram all these multiplexers in between multiple layers of these things? That is, that's a nightmare, okay? You know, I'm actually thinking in advance. That is something I've not done yet. This is my first time thinking ahead. we'll burn the bridge of how we're gonna do the next layer, because I'm thinking about we're gonna shove the multiplexer in between this layer. But we'll get to that when we get to that. So if we actually get to the multiplexer in today's stream, I'd be surprised. I think we're gonna get to the multiplexer on Saturday. Well, I'm gonna get to it. I don't know if I'll stream on Saturday. Can't guarantee when I'm gonna stream because I have a really weird schedule that just isn't actually a schedule. It just don't expect streams. They happen randomly when I feel like streaming. Okay. Alright. So, yeah, basically this is what building a computer is like in Minecraft. You just build the same part over and over again until you build the next part, which is, yeah. So this will basically be the whole ALU done in less space and with less wiring than the other one. Because we're just going to use the same signals up to the top. And hopefully it will be a bit more synchronized, because we do need to sync these things up. So that way they work properly. All good and proper. Okay. Now this one is going to be AND. Or is it going to be NAND? It's not NAND, because NAND is off. But it's not AND, because AND is off. So this is... Oh, wait. No, it is NAND. Neither this one or that one are on. Alright, we're making some good progress on this thing. And the good thing is that these logic gates are really easy to build compared to the actual adders, which takes so long, and then you need to test them because you never know when you've messed them up a bit. But hey, maybe someday I'll be better at building these things instead of messing them up every single time. And we actually don't need that pink bit there. That pink bit was just... That just looks silly. We just need this. This is all you need to make a nice little computer thing. And when I mean little computer, and I should turn this into shorts. I should, like, cut all these good jokes about computers into shorts. That'd be a very good idea. But, actually, that's not my original idea. That's not the original idea. Or, it's not an original idea. Basically. At one point in time, somebody actually suggested during a stream that I should turn the stream into a bunch of shorts afterwards. So that way, they could watch the highlights. Which is, a good idea. But I honestly don't... I'm too lazy to actually bother doing that. So that's why I don't make shorts out of my streams. I don't want to edit the stream. I'd have to download it, and I don't want to download a stream that's like 3 hours long, and is about and watch the whole 3 hours over again. Because when you're editing a video, right? It's about like you're just watching your own video. And putting a little bit of flair on it. Which is, I mean, it can kind of get boring if you're just watching the same section over and over again. It's also kind of interesting to watch my own videos. I'm not sure why I find my own videos interesting, but I sometimes occasionally watch them. Especially the older ones, because it's like, oh man, I've come so far. But yeah. So yeah, my current benchmark for how far I've come is, I don't know. I don't know how to measure how far I've come. That's a very good question, actually. I don't actually have a benchmark to measure how far I've come. Well, actually, I do. I just measure it by how close my older videos are to how I am today. It's kind of weird, but, like, you see... let me get the words out here before I just mess all the words up. But basically, when I record, or when I used to record, no, that's not how I'm gonna start off this sentence. I don't know how I'm gonna start off this sentence, but let me just think for a few more minutes, and then I'm sure I'll be able to get this sentence out. So basically, what was I saying? I was saying that, okay, yeah. The benchmark for how I measure myself as a creator is how I was compared to how I am today. So, basically, when I look back, if my videos were less good than they are today, then I have